Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video I'm going to talk about an infinitely repeated version of the Cournot model of oligopoly. We're going to return to the specific example that we went through in the videos introducing the Cournot model. In this example there are two firms, each with a cost function C1 of Q1 and C2 of Q2. Firm 1's cost function is 40Q1 and firm 2's cost function is 40Q2. The inverse demand function is P of big Q equals 160 minus Q over 2, which we then plug in little q1 plus q2 in for the big Q to get 160 minus q1 plus q2 over 2. Instead of these firms interacting just once, we're going to have them continue to do it over and over and over, which is going to allow us to apply the Grimm trigger strategy. To determine whether the Grimm trigger strategy will allow the firms to collude over time, we're going to do a similar analysis to what we did in the previous video. We need to figure out the present value of following the strategy and figure out the present value of defecting and see which one is better. To do that, we are going to need three pieces of information. First, we need to know the profit that the firms will get from colluding, and I'll define that as pi collude. Then we need to know the Cournot profit, because once the Grimm trigger is pulled, we're going to go back into the Cournot Nash equilibrium outcome. And then finally, we need to know the profit that we get from defecting. And then we're going to use the present value formula to incorporate all these pieces of information to figure out if it's possible to collude. Since we already covered this example previously, I'm going to go through this math relatively quickly. First, let's think about what happens if the firms collude. This means that the two firms are going to be behaving together as if they were a monopoly. And so we're going to set up a profit function like they were a monopoly. So we have total revenue, price times quantity, price given by our inverse demand function, minus total cost of 40Q. I'll do a little bit of cleaning up here and combining terms to get 120Q minus Q squared over 2. To maximize profit, we take the first order condition, which is the first derivative, set equal to 0. So we get 120 minus Q equals 0, which gives us a monopoly quantity of 120. The monopoly price we get by plugging 120 into our inverse demand function, so we get 160 minus 120 over 2, which is 100. Of course, this is not actually a monopoly. It's two separate firms that are acting together as if they were a monopoly, so they're going to split this 120 in half. And so that's going to give us little q, collude, equals qm over 2, which in this case is 120 over 2, or 60. The profit that each firm makes from colluding is going to be total revenue of 100 times 60, minus a total cost of 40 times 60, which is going to come out to 3,600. That is the first piece of information that we needed. Now let's do the Cournot Nash equilibrium. For this, I'm going to use firm 1 as a representative firm and just write their profit function, which is 160 minus Q1 plus Q2 over 2. All that times Q1, that's our total revenue, and our total cost, 40 Q1. Multiplying this whole thing out and combining terms, we're going to get 120 Q1 minus Q1 squared over 2 minus Q1 Q2 over 2. For their first order condition, we need to take the partial derivative of pi 1 with respect to Q1, which is 120 minus Q1 minus Q2 over 2 equals 0. From here, we can get our best response function by adding Q1 to both sides, which is going to give me Q1 star equals 120 minus Q2 over 2. From here, we could do the same thing for firm 2, but since we have complete symmetry in this problem, I'm going to apply symmetry and state that we know that in equilibrium, we're going to have Q1 equals Q2 equals Q Cournot. And so I'm going to replace the Q1 and Q2 here with Q Cournot, 120 minus Q Cournot over 2. Add Q Cournot over 2 to both sides, I get 3 halves. Q Cournot equals 120. Multiply both sides by 2/3 is going to give me Q Cournot equals 80. Each firm is going to produce 80 units of output. To get the price, I'm going to plug in 160 minus Q1 plus Q2 over 2, which is going to give me a price of 80. Calculating each firm's profit, we have pi Cournot is price times quantity minus total cost, 40 times 80. That comes out to 3,200. That is the second piece of information that we need. Note that when firms are competing in the Nash equilibrium, they're making 3,200 profit, which is less than the collusive profit of 3,600. And so they do have some incentive to try to collude. The last thing we need to do is figure out what the defection profit is going to be. Let's say that firm 1 thinks firm 2 is going to collude. In that case, firm 2 is going to produce half the monopoly quantity, which is 60. If firm 1 is going to defect, they're going to try to make as much profit as possible, meaning that we need to plug 60 into firm 1's best response function, which tells us that the defection quantity is going to be 120 minus Q2 over 2, 60 over 2, and that gives us 90. Note that this is higher than the Cournot quantity of 80. To get the price when defection happens, we're going to plug these in to our inverse demand function. 160 minus Q1 plus Q2, so we have 90 and 60 here, divided by 2. That's going to give us 160 minus 75, which is 85. And the profit that the firm that defects gets is 85 times 90 for the revenue, minus 40 times 90 for the total cost, and that's going to give us 4,050. We don't explicitly need this information, but let's calculate the profit for the firm that got defected on. In the example that I gave here, that was firm 2, so I'm just going to say that's firm 2's profit. But it could easily be firm 2 defecting on firm 1. It doesn't really matter because this problem is symmetric. That firm still faces the price of 85, but they're only producing 60. And that gives us a total profit of 2,700. We aren't going to use this number later. What we really were here to get is this third and final piece of information that we needed, the defection profit. Now we're ready to lay out the Grimm trigger strategy for the Cournot model. As always, that has 3 parts. Part 1, in the initial period t equals 0, we're going to do the cooperative action, which in this case is to produce the collusive amount of output we called Q collude, which was 60. Part 2, in the subsequent periods, which we are going to call t greater than or equal to 1, then we're going to produce the collusive output Q collude, again 60, if the other firm produced 60 in all previous periods. Part 3, in the subsequent periods greater than or equal to 1, this is the trigger part where we are going to produce the Cournot Nash equilibrium output of 80 if the other firm ever produced a quantity other than 60 in any previous period. So this lines up with what we know about Grimm trigger, where we are going to be cooperative as long as the other firm has always been cooperative in the past, but if they ever break that trust, it's gone forever, and we are always going to produce 80 forever. Now let's see if it is possible to get a Nash equilibrium by using the Grimm trigger strategy. If both firms are following Grimm trigger, they're going to initially attempt to collude. In the subsequent periods, they're going to just continue colluding with each other because nobody has pulled the trigger. Nobody has tried to defect. As we did in the previous video, I'm going to use a big pi Grimm to denote the present value of the entire profit stream when using Grimm trigger. We're going to get our collusive profit in the initial period. We're going to get the collusive profit in t equals 1. We're going to get the collusive profit in t equals 2, and so on forever. Using the geometric series formula, that's going to give us pi collude plus pi collude over r. Thinking about our example, we have 3600 plus 3600 over r. Now let's see what happens when we have one firm defect. The other firm is still playing Grim Trigger, so in the initial period, they are producing 60 and our defector produces 90, gaining that big burst of profit that we calculated a minute ago, which is pi defect. But as soon as this happens, in all the subsequent periods, the other firm is going to drop into Grim Trigger punishment mode and produce 80 for the rest of eternity, and so the defecting firm's best response to that is to just produce 80 as well, giving them the Nash equilibrium Cournot profit forever. And so that's going to happen in period 1. We're going to get pi Cournot in period 2, and so on forever. Again, using the formula for the geometric series, we're going to get pi defect plus pi Cournot over r. Now, plugging these in for our specific problem, what we get is 4050 plus 3200 over r. We now have our two competing payoffs. Grim Trigger can give us a cooperative Nash equilibrium if the Grim Trigger present value is greater than or equal to the defection present value. As in our previous video, the Grim Trigger strategy can sustain a cooperative Nash equilibrium if that present value of the entire profit stream for Grim Trigger is greater than or equal to the present value of the profit stream from defecting. Filling these in, we have 3600 plus 3600 over r greater than or equal to 4050 plus 3200 over r. Now we just need to do a little bit of algebra here, so I'm going to subtract 3600 from both sides, and that's going to give me 450 over there, and then subtract 3200 over r from both sides, and that's going to give me 400 over r over here. Next, I'm going to multiply both sides by r and divide both sides by 450, and that'll give me r over here, and over here 400 over 450. As before, I'm going to flip this around for convenience to get r on the left-hand side. So r is less than or equal to 400 divided by 450, which is 8/9. This gives us an upper limit on the interest rate that is possible to get a Nash equilibrium where the firms are colluding. Defection offers an initial big burst of profit in exchange for a lower amount of profit in the future, whereas Grim Trigger, we get a medium amount of profit now and a medium amount of profit going forward. Defecting is better when we have a relatively high interest rate, because that makes the future profit less valuable relative to now, and so that big burst of profit right away is more attractive. On the other hand, when interest rates are low, we would prefer to get this steady stream of profit instead of the big profit now in exchange for the smaller profit later. And that cutoff point is 8/9, or about 89%. The last thing I want to mention here is that this collusion occurs purely out of self-interest. Both players are playing strategies that maximize their profit by using Grim Trigger, as long as r is lower than 8/9. Firms do not need to communicate with each other and come to an agreement to restrict output to 60. They did it on their own by realizing that this is the best way to make profit, and by threatening each other with the Grim Trigger strategy. As long as the interest rate is sufficiently low, the threat of punishment in the future is enough to get the firms to cooperate. But they don't need to communicate, which is why we call it tacit collusion. In the next video, I'm going to wrap up our discussion of this topic by talking briefly about finitely repeated games.